Hello, dear students. Glad to meet you again in this session. Now, in this session 1.6, we are going to discuss about Dalton's atomic theory and atomic and molecular masses in chapter 1, some basic concepts of chemistry, grade 11. Before getting into this session, let us recall what are all the topics that we have discussed in the previous sessions. In the first session, we have discussed the importance of chemistry and nature of matter and its classification. In the second session, we have discussed the 7 basic units of SI system and its symbol. In the third session, we have discussed about the measurements of matter and some physical quantitative properties like mass, weight, volume, density, and temperature. In the fourth session, under the heading Uncertainty in Measurements, we have discussed about the scientific notation, significant figures, precision and accuracy, and dimensional analysis. In the fifth session, we have discussed about the laws of chemical combination, learning outcomes. At the end of this sixth session, students, you will be able to list the postulates of Dalton's atomic theory, define atomic mass, define molecular mass, and explain formula mass. By observing the laws of chemical combination that we have discussed in the previous session, French chemist John Dalton published a new system of chemical philosophy in which he proposed some important points. Let us see those points one by one. Students, we know that anything that has mass and occupies space is called matter. Dalton proposed that matter is made up of extremely small indivisible particles called atoms. Next, he proposed that atoms of same substance are identical in all aspects. For example, they possess same size, shape, mass, and chemical properties. Chemical properties are nothing but the chemical nature or the chemical behavior of the element. Next, atoms of different substance are different in all aspects. For example, they possess different size, shape, mass, and the chemical properties. The chemical nature of sodium will be entirely different from hydrogen, oxygen, nitrogen, and copper. Like that, the chemical nature of oxygen is entirely different from hydrogen, nitrogen, copper, and sodium. Next, he proposed that the smallest particle that takes part in a chemical reaction is an atom. He proposed compounds are formed when atoms of different elements combine in a fixed ratio. So here we could see 2 parts of hydrogen combines with 1 part of oxygen to form 2 parts of water. Whatever may be the source, whether it is a tap water or well water, the ratio of hydrogen and oxygen in water molecule will be 2:1. Chemical reactions involve reorganization of atoms. So he proposed that atoms can neither be created nor destroyed in a chemical reaction. Here you could see the elements that present in the reactant side gets reorganized in the product side. So these are all the postulates of Dalton's atomic theory. Atomic mass. Before getting into this topic, let me explain the word relative. Here you could see 2 pictures. If we compare picture 1 and picture 2 is twice as that of picture 1. It means picture 2 is relatively twice that of picture 1. In the same way, in the 19th century, scientists could determine the mass of one atom relative to another atom by experimental means. Hydrogen was used as a standard to find the atomic weight of other elements because it is the lightest element. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to hydrogen. Later, they discarded hydrogen because it is a gas and it does not have neutrons, and hydrogen forms stable compounds only with few metals. So nowadays they have taken carbon 12 as an arbitrary one. In session 2, while discussing about the SI system, I have explained why scientists have selected carbon 12 as a standard one. Why they have selected carbon 12? Because carbon 12 has 6 protons and 6 neutrons. They are responsible for mass. Most of the compound available in nature contains carbon, and carbon 12 is present 99.89% in nature, and carbon can exist as atom and it is in solid state. So they have selected carbon 12. In 1961, the International Union of Chemists selected the most stable isotope of carbon 12 as a standard to determine the relative atomic mass of other elements. The atomic mass unit AMU or unified mass may be defined as 1/12 of the actual mass of an carbon 12 isotope in its ground state. Why they have given 1/12 of the actual mass? Because we know that carbon 12 has 6 protons and 6 neutrons. So totally it has 6 plus 6 equal to 12 units. So 1 unit of carbon is equal to 1/12, right? So they have given 1/12 of the actual mass of carbon 12 isotopes. Today, atomic mass unit, that is AMU, has been replaced by U, which is known as unified mass. One atomic mass is approximately equal to 1.6605 into 10 to the power of minus 24 kilogram. Average atomic mass. Before getting into this concept, average atomic mass, let us see what is an isotope. Many naturally occurring elements exist as more than one isotopes. What is the meaning of isotope? Isotopes are nothing but elements that has same atomic number but different mass number. Atomic number is nothing but number of electrons, and mass number is nothing but the sum of protons and neutrons. In this picture, you could see carbon has same atomic number, that is same electron number of electrons, but has different mass number. So here, that's why we are having 3 isotopes in carbon: carbon 12, carbon 13, and carbon 14. So, to calculate the average or relative atomic mass, we have to take into account the existence of all these isotopes and its relative abundance. Relative abundance is nothing but percentage occurrence. So, we need to multiply percentage occurrence with atomic mass. When we say percentage, it is for 100. That means the amount present in 100 parts. So this 98.892 represents the amount present in 100 parts. Now to find out for one part, we have to divide this decimal by 100. So it becomes 0.98892. Then in the case of carbon 12, we have to multiply 0.98892 by 12. Likewise, for carbon 13, we have to multiply 0.01108 by 13.00335. In the case of carbon 14, 2 into 10 to the power of minus 10 divided by 100, we can write this number as 2 into 10 to the power of minus 12. So we have to multiply this relative abundance of carbon 14 with the atomic mass of carbon 14, 14.00317. The relative or the average atomic mass of carbon can be calculated as follows. For this, we need to take the relative abundance of all the isotopes and the atomic mass of all the isotopes of carbon. First, we have taken the relative abundance of carbon 12, 0.98892 into 12. This is the atomic mass of carbon 12. When we multiply these two numbers, we get 11.867. Coming to the next one, this is the relative abundance of carbon 13. So 0.01108 has to be multiplied with the atomic mass of carbon 13, that is 13.00335. When we multiply these two numbers, we get 0.144. Coming to the last one, this is the relative abundance of carbon 14. So 2 into 10 to the power of minus 12 can be written as 0.0012. If we multiply this number with the atomic mass of carbon 14, which is 14.00317, we get the answer 0.001. When we add all these numbers, we get 12.012, which is the average or the relative atomic mass of carbon. We have taken another example, chlorine. Chlorine also has two isotopes. They are chlorine 35 and chlorine 37. The relative abundance or the percentage occurrence of chlorine 35 is 77 and chlorine 37 is 23. Percentage means for 100 parts. Now we need to calculate for one part. So we have to divide this 77 by 100. We get 0.77 for chlorine 35. And we have to divide 23 by 100. We get 0.23 for chlorine 37. The relative or average atomic mass of chlorine can be calculated as follows. As we have done previously in the case of carbon, here also we have to calculate by multiplying the relative abundance with its atomic mass. So here first we have taken chlorine 35. This is the relative abundance of chlorine 35, 0.77, and this is the atomic mass of chlorine 35. When we multiply these two numbers, we get 26.95 plus this is the relative abundance of chlorine 37, 0.23. We have to multiply this with the atomic mass of chlorine 37 is 37. When we multiply these two numbers, we get 8.51. When we add these two decimals, we get 35.46, which is the relative or average atomic mass of chlorine. Molecular mass. Molecular mass is the sum of the atomic mass of the elements present in a molecule. So to calculate the molecular mass, we need to multiply the atomic mass of each element by the number of its atom and add them together. Here I have taken methane as an example. In methane, we have one carbon atom and 4 hydrogen atoms. Methane molecule contains one carbon atom and 4 hydrogen atoms. The molecular mass of methane can be calculated as follows. Its formula is CH4. What is the atomic mass of carbon? It is 12.011. So here we have only one carbon. So we need to multiply the atomic mass of carbon by 1 plus how many hydrogen we are having here? 4. So what is the atomic mass of hydrogen? It is 1.008. So we have to multiply the atomic mass of hydrogen by 4. So when we add these two decimals, we get 16.043, and that is the molecular mass of methane. Formula mass. Before discuss about formula mass, let us take sodium chloride ionic compound as an example and see the ionic entities in sodium chloride. Sodium atom has 11 protons and 11 electrons, and chlorine atom has 17 protons and 17 electrons. While forming this ionic compound, sodium donates one electron to chlorine, which is in its outermost orbit, and becomes a positive charge. Chlorine accepts this electron from sodium and becomes negative charge. And in this compound, ionic compound, the positive and the negative entities, in our case, sodium and chloride, positive and the negative entities are arranged in the three-dimensional structure as shown in the picture. So in the case of ionic compounds, the formula of that compound represents its positive and negative entities in three-dimensional structure. Its formula does not represent its molecule. It represents only the ratio of different ions in the compound. So instead of molecular mass, we use the term formula mass for such compounds. Formula mass of an ionic compound is obtained by adding the atomic mass of all the atoms in a formula unit of the compound. Here, the formula mass of sodium chloride can be calculated by adding the atomic mass of sodium and the atomic mass of chlorine. The atomic mass of sodium is 23.0 U. What is the atomic mass of chlorine? It is 35.5 U. So, by adding 23.0 U and 35.5 U, we get 58.5 U. That is the formula mass of sodium chloride. Students, let's recall the topics that we have discussed in this session. We have discussed the postulates of Dalton atomic theory, atomic mass, molecular mass, and formula mass. Hope this session is useful to you. See you soon in the next session. Have a nice day. Thank you.